Hello YouTube and welcome to What the Math. In today's video we're going to be using two video games, Space Engine and Universe Sandbox 2, to talk about a topic of solar classification, which is basically classifying our stars. Here's a star, that's our sun right here. And we're going to be talking about how we classify them and basically how they're different and what it all means in terms of astronomy. Now, before I start, I'm going to erase all of this and create a completely new solar system. We're going to start from scratch, and actually when I say scratch, what I mean is this. We're going to start with Jupiter. Why Jupiter? I'll explain it to you in a second. So Jupiter is, as you probably are aware, a gas giant. It's basically an object that's almost entirely hydrogen. There is a bit of silicates and a bit of other stuff in it, but for the most part it's just hydrogen. Now, what will happen to Jupiter if you basically start adding more hydrogen to it? Let's find out. So here's our Jupiter, and I've decided to increase its mass by 11 times, 12 times, and 13 times. And as you can see, it suddenly changed its shape a little bit. Now in this game it's simulated quite well in terms of the critical mass. So as you increase this, you'll see that the temperature of Jupiter will start increasing as well. If you look at the surface temperature, it's suddenly no longer minus 273 degrees anymore. It is now almost 100, 110, 120 degrees. As I increase the mass, the temperature increases as well. And interestingly, you can still see the, where is it? You can still see the spot on Jupiter there. Anyway, so let's keep increasing the mass of Jupiter, and at around 50 times the mass of actual Jupiter, you'll see that the temperature will reach a point where the what will happen is, because of the amount of stuff inside Jupiter and because of all of this crazy mass, it will get such a huge temperature and such a huge pressure on the inside that it will actually start glowing. And there we go, it starts glowing and it slowly starts transforming. Now this is, well, no, not yet. This, approximately here, this is where it now becomes something called a brown dwarf. So it's no longer a gas giant, even though it says gas giant right here. It is now technically a brown dwarf. What is a brown dwarf? Well, it's technically a star. It's a star that was not big enough or not massive enough to acquire enough material to start fusion process, which basically why we have stars, why they're so bright and why they produce so much heat. And fusion is basically a process by which atoms combine into other elements, and this is what happens inside our sun as well. So this was not big enough to start fusion, but it's still big enough and massive enough to have this internal temperature due to pressure. And so it starts glowing from the inside and it becomes a brown dwarf. And so say hello to brown dwarf Jupiter. This is what Jupiter would look like if it was approximately 64 times the mass that it has now. Now today we actually use a very specific classification scale to try to classify various stars. And then the scale that I'm talking about is known as Morgan-Keenan scale, also known as MK scale. Basically it has these letters that it uses to classify various stars based on their, well, it's a combination of temperature and also the color or the spectrum that they emit, but specifically the temperature. So up to about 2400 degrees Kelvin, this would be still a brown dwarf. So let's actually keep going, keep increasing its mass, and look at how beautiful it is, until it reaches almost 2400 degrees. And almost there, so at 91, possibly 92 masses of Jupiter, we're going to reach the requirement for this to become the next stage. And almost there, 95, and at almost 100, it's 98.5 masses of Jupiter, and you get something called a red giant. So this is a Jupiter as a red giant. Now these are actually the most common stars in our solar system, and this is not what our sun is. Actually, this is not our sun. but these are very, very common. There's actually so many of them. There's, according to astronomers, there's something like 77% of all of the stars in our galaxy, or I guess in our universe in a sense, would be this type. They would be red dwarfs. So this is when you have a star that's, if you look at the mass of it compared to our sun, it's about 10% of our sun, and it is much less bright and much less hot as well. And according to MK scale, this is the M type of a star, and I'll show it to you in Space Engine as well. You'll see what it looks like. And here is an example from Space Engine. This is what a red star looks like. This is a star code Gliese 176. So it's a red star. It's not too luminous. It's not too bright. It doesn't actually hurt your eyes yet. And also it's not particularly big. So compared to our sun, it's much less brighter and much less hot as well. And actually, just to make this a little bit more interesting, let's actually add Earth at a distance of where it is in our solar system and see how much this star will warm up our planet. So if we had an M star type of a star, how warm or how cold would our Earth be? And here we go, we have an Earth orbiting around an M type of a star, and look at that, it's entirely frozen. The temperature is minus 110 Celsius, and there's nothing but ice on it. So this is actually what it would look like from Earth if you were to look at our star called Jupiter. So yeah, it's not very bright, it's not very strong in terms of heat, and basically it would not really help us to survive either. Alright, let's keep going. So the next class, okay, let's keep going, and we're going to add a little bit more mass, and it finally became an actual star. So after about 3700 degrees Kelvin, it becomes the next class. And the next class is called the K class. So right about here. So at 262 masses of Jupiter, it becomes something we call a K class. So the temperature is just over 3700 degrees Kelvin. Our Earth will start warming up, and this is a much brighter star, but still not as bright as our sun. There's approximately 12% of all of the stars in our galaxy that are this type of a star, and it's a little bit brighter, it's a little bit hotter, but still not as hot and not as bright as our sun. But the Earth that we just made might benefit more from it, and so if I accelerate time, you'll see that it will start slowly warming up. Or actually, maybe not. Maybe I'm totally wrong and it's still cooling down. Look at that. So even a K-type star would not be enough to warm up our planet at the same distance as it is now. So let's actually see what it looks like in Space Engine. And this is probably just a little bit brighter and just a little bit more orangey. And here is an example of this type of star in Space Engine. This is also known as an orange dwarf. So this is a K-type star. Basically, it's a little bit more orange than the one before this, but still not as bright as our sun, and it's absolutely gorgeous and absolutely beautiful. Alright, so what is the next type? And the next type is the G type. So this is what our sun actually is. It's called a yellow dwarf. So if I increase the temperature, by increasing the mass of course, if I increase the temperature to approximately 5200 degrees Kelvin, this is when, actually I can just do this. Change this to mass of sun, and then increase this way. There we go. At approximately, there we go, it's coming close to, there we go. So at approximately 89% of the mass of our sun, it becomes the yellow dwarf. So this is what our sun is like, and now our Earth will probably, or hopefully, start warming up, because now our Jupiter is a star that is very similar to what we have, or what we are orbiting around, so basically our sun, and it's the brightness and the heat that we're actually used to. So obviously if you go to Space Engine and try to look at it, and if we just basically type Sol, that's the official name of our star, we'll see that this is what it looks like. And this is an example of a yellow dwarf. Okay, so that's basically what we're used to the most, and there's approximately 7-ish% in our galaxy. Now, once the temperature increases past 6000 Kelvin, that's when it becomes the F-type. So this is the F-type star, and this is also known as the yellow-white star. So I'm actually going to see how my Earth does in relation to this star, and let's see how much it heats up. And here we go, our Earth has warmed up and is now getting really hot. It's already at 36, 37 degrees Celsius and it's still warming up, 40 degrees Celsius average. All the ice caps are gone. If we actually look at the ice caps, there's no ice left whatsoever. So, oh, we're already at 47. So basically, if we had an F type of a star instead of our sun, we would have some serious trouble with heat. There's almost no ice left. I think there's actually no ice left. Yeah, all of the ice is gone. Everything has melted. There's just water. So the sea level. Oh, actually, maybe there's some ice here. But this sea levels would increase dramatically, and we would have some serious weather conditions. Alright, let's keep going, and the next type is the A type of a star, and this is at 7500 degrees Kelvin. I should probably keep this. If you keep the radius stable, your star will not actually go into supernova, because otherwise it will. Okay, so, oh, I missed it. Here we go. No, here we go. So this is the A type. And the A type is also known as the white star. So I'm going to let this run for a few minutes just to see how hot my Earth gets. But let's actually find the A type in Space Engine. Oh, and F type as well. And I believe this right here, there we go. This right here is an F type star. So it's slightly brighter than the sun. And the next one will be the A type. And here we go with, this is the A type, this is the White Dwarf, so it's quite a lot brighter. You can see the luminosity here is 20 times the luminosity or the brightness of the sun. So this is quite a different sight from what we saw before. And there's actually not that many of these stars either. There's only about less than 1%, it's about 0.6% of all of the stars in our galaxy are basically this type. And let's see how our Earth is doing. Let's actually zoom in on it. And our poor planet is getting really toasty. It's at 80, 85, 90 degrees Celsius and still going up. Yeah, there's going to be, oh my god, look at that. Everything is scorched. Nothing is green anymore. Okay, so that's not a good sign. All of the plant life, all of the, basically everything has been scorched, and we're about to lose our water as well. And the water has started to retreat, so Black Sea is getting evaporated, White Sea is gone, Great Lakes are gone, there's a huge gap in the Mexican Gulf as well. So basically, yeah, it's getting a little bit too hot, it's already 106 degrees Celsius. Let's actually see how hot it gets after a few years. Well, it is still getting hotter and hotter, and almost all of the water is already gone. So yeah, and that's only the A type of star, that's only the White Dwarf. There's still a little bit of water left in the Indian Ocean, in the Atlantic Ocean, and a little bit in the Pacific Ocean. But yeah, so that's basically the end of life on Earth, or most of the life on Earth. And it even started to evaporate a little bit because of the heat from this newly created Jupiter star. Okay, so let's keep going and go to the next type, which is the B type. And to get to the B type, we need to have at least 10,000 degrees Kelvin, which is somewhere right here. There we go. And this is the blue-white type, or the B type star, which is really rare. There's only about 0.1% of these stars in our galaxy, and they're quite massive. They're usually at least 2.2 or I guess over 2 masses of sun, and usually when these stars end, they'll produce either a neutron star or a black hole. Alright, let's find a B type of a star here in Space Engine and see how bright it is. Usually they're ridiculously bright. They're actually one of the brightest objects in the sky. Okay, so let's see. There's quite a lot to choose from actually. Actually, let's do it the other way. Let's actually look for one that's the most famous one. And that's the Rigel. Rigel is the most famous B type of a star. There you go. It's called Blue Luminous Supergiant. And in this game, you'll see how bright it is. There you go. So it's blue-white, it's ridiculously bright, You can see luminosity is 39,000 times the luminosity of the sun, so it's 39,000 times as bright as the sun. It's also very, very hot. It's almost 11,000 degrees Celsius. So this is basically your B-type star. And obviously, if we had a B-type star instead of our star, instead of sun, the Earth would probably start melting. I'm going to let this run for a few more years just to see how hot it is going to get if it had a B star instead of sun. And with a B type of a star, our Earth would be approximately 370 degrees Celsius. It would kind of look like this, like a scorched toast with basically no water, nothing on it. And it's sort of similar to what Mercury is right now as well. So basically it would be completely scorched, black and empty. And so that is a B-type, but that's not it. There's actually another type that is really, really rare, and that is really, really, really big and really, really, really bright. And the type that I'm referring to is called the O-type. These are the super rarest of the stars. They're the most massive, the most hot, the most luminous stars in basically anywhere, everywhere. And these stars, let me just try to find one. These stars are massive. They're ridiculously big and ridiculously bright. And here's the example of that type of star, O star, in Space Engine. Basically a ridiculously bright, super gigantic star called Mesa. This is from our solar system as well, and everything is white because I'm right in the middle of it. There we go. So basically it's ridiculously bright. So let's actually try to make this in Universe Sandbox. Now the thing is, in Universe Sandbox, if you reach a certain mass, in terms of solar mass, you will most likely initiate a supernova. So I'm going to try to avoid that, but let's see if I can actually try to make this into an O star or O-type star. And to become an O-type star, the temperature here has to be at least 30,000 degrees Kelvin. So I don't know if I can actually get that without the supernova, but I'll try. Usually, as you get closer and closer to that limit, you start getting the supernova effect. And then basically, oh yeah, and all of these stars after the supernova, they always become black holes. So this will actually become a Jupiter black hole. Okay, so getting closer. 17. Let's see if we can do it. 18. Okay, well that didn't really work. So I unfortunately caused supernova. The maximum I could reach was 27,000 degrees Celsius, which is close to 27,000 Kelvin. And unfortunately, in this game, it's really hard to simulate the O-type star. I'm gonna try it again just for fun, but basically, yeah, when an O-type star goes through supernova, it leaves behind nothing but a black hole, and these are usually very massive black holes. So now we have... Where's our Earth? What happened to our Earth? Oh no, where is it? I lost my Earth. The Earth, if it's still somewhere around here, is orbiting a black hole and is probably in the middle of the supernova, meaning that it's probably ridiculously hot. No, I think it's gone. I think our Earth is finished. I think it must have disappeared with the supernova. Alright, so let's actually try this again, but this time in the opposite direction. And just to kind of go backwards and put this all together, let's take a look at them all side by side. So this right here is a B-type star, and basically this is the biggest one we can do in this game. It doesn't allow us to make an O-type because everything just goes supernova. So this is the super massive, super bright type of blue-white star. Then we have an A-type star right here. It's slightly smaller but still quite bright. Then we have the F-type. This is around 7,000 degrees Kelvin. Then we have G-type, which is similar to our sun, or basically this is our sun. I changed the name. After that, we have K-type, which is slightly less massive, less bright, and less hot. And the last type, or the least bright, was the M-type. Now, the brown dwarfs are not in this classification, but we're going to make another. We're going to put another star right here and make it a brown dwarf. So to be a brown dwarf, it has to have a temperature of less than 2400 degrees Kelvin. So once it goes down to about 2000 Kelvin, it is then considered to be a brown dwarf. So technically not even a star, basically sort of like a combination of gas giant and a star. Okay, so to make this into a brown dwarf, I actually have to unpause the game, and it will become a brown dwarf, but unfortunately, if I unpause my game, well, let's actually find out what happens. All of these stars will start acting really funny. They'll start orbiting in a very interesting fashion, because I believe I did not really set them in orbit. Let's actually see what happens. It's going to be quite an interesting dance of the different types of stars. And my money is on a B type. I think the B type will probably take over because it's the most massive one. B and A, they're already kind of orbiting around each other, so here we go. And let's see how our brown dwarf is doing. Oh, it's getting a little bit hotter. And surprisingly, none of my stars collapsed into each other, and this one is now a brown dwarf as well. So this is our brown dwarf right here. So not really a star, but not really a gas giant either. And it's orbiting around the M-type star, so it's actually going to get even hotter because it's right next to the star. The other stars are just flying around each other, and these guys are dancing with each other really nicely. So this is now a binary system, and there's actually there are some stars that we found that do have a B-type and an A-type orbiting in such a fashion, and they're actually ridiculously bright. They're some of the brightest stars in the night sky. So basically that's it for the solar classification and the different types of stars that we have and that you could make in the game, and how to make them and how to convert your gas giants into stars and vice versa. Alright, thank you for watching, please subscribe, and game you later, alligators. Bye bye.